This tutorial is intended to demonstrate the use of ReactLab Kinetics to model and analyze a complex mechanism in coordination chemistry. It illustrates several more advanced features of ReactLab, including the ability to include both kinetically observable rates and rapid equilibria in the reaction model, and also to correctly compute and model pH changes associated with protonation steps. It also illustrates the use of auxiliary parameters. The reaction involved is the stepwise reversible formation of the complexes Ml and Ml2 from a monodentate ligand L, ammonia in this example, and a metal M, such as nickel. A complication arises from the fact that in aqueous solution, the ligand is also involved in a protonation equilibrium. And to make things more interesting, a limited amount of buffer has also been added to the solution. Let's start the demonstration by running ReactLab Kinetics. Here is the main GUI, from which we can load the demonstration workbook. The data are organized in the data worksheet. The time course of the kinetics is defined in the first column and the spectral wavelengths, the top row. The Excel chart shows the complete set of kinetic profiles. If we now switch to the main worksheet, we can see the model representation of the reaction scheme I showed earlier that we are fitting to the data. Here are the complex formation steps. The forward and reverse rates for the metal ligand binding equilibria have been entered in the first four lines using the forward arrow symbol. These represent kinetically observable processes. Again, note that the reverse steps use the forward arrow symbol but with the species names in reverse order. The protonation equilibrium of the ligand is effectively instantaneous and represented by the equal sign. The buffer equilibrium is represented in the same way. The parameter provided is the log of the actual equilibrium or formation constant, as this is computationally more robust than using the absolute value. I have also added some helpful text labels to the individual reaction steps for reference. It should be noted that the log of the buffer association constant is numerically equal to the buffer pK, since this is derived from the acid dissociation constant, whereas ReactLab requires all equilibrium constant to be presented as association constants. I will now introduce a unique feature of ReactLab, the use of auxiliary parameters and Excel formulas to define special parameter relationships. In this example, we want to define the rate constants of the back reactions as a function of the fitted forward rate constants and independently known equilibrium constants. So we introduce these as auxiliary parameters. The entry in the parameter cell corresponding to K minus ml is an Excel formula, F7 over 10 to the power of K7, which refers to the forward rate Kml and the equilibrium constant log Kml in the auxiliary parameter list. A similar formula entry has been used to create an equivalent dependency for K minus ml2. Only the two rate constants for the forward reactions are fitted in this example, though you will observe the reverse rates change during the fit because of the auxiliary parameter relationship. Having provided all the parameter information, it is also necessary to define all starting concentrations and spectral contributions of the defined species. In this example, only the metal-containing species are coloured. All others, including the buffer components, are non-absorbing. The values for the initial M and L concentrations are straightforward, but the initial concentrations of the species in the protonation equilibria require further explanation. During the progress of the kinetics, the protonation equilibria are always updated according to the prevailing relevant concentrations, including at time zero. The species that take part in the protonation equilibria are L, H, B, LH, BH and OH. To compute the actual protonation equilibria position, ReactLab needs to know the total concentrations of the components, which it can work out from these entries along with the protonation constants. It should also be noted that the OH species is introduced automatically if protons, H, are included in the mechanism. The equilibrium defined by the ionic product of water, Kw equals H times OH, is then included in the computations to correctly model pH changes. The fitting from reasonable initial guesses for the two second-order rate constants is straightforward and results in KML equal to about 1000 and KML2 equal to about 500, both of which values are correct. I will just reset the fitted parameters to demonstrate that this data does allow the determination of these two second-order rates. I will adjust KML to 400 and KML2 to 300. We can now switch back to the main GUI and perform an update to see how well the model with these altered parameters matches the data. We can see some structure in the 3D residual surface now and some distortion in the species spectra. We will use this as a starting point for the fit. The fitting is iterative, and as you can see, we converge to a minimum square sum. The residual surface is now random, and we have clean spectra. All of the results and optimized parameters have been written back to the Excel workbook, and if we now go to the results sheet, we can inspect some graphs that have been generated in Excel. It is interesting to inspect the concentration profiles in some detail. The complex species behave as expected, with some equilibrium reached that includes a small amount of free metal, some Ml complex and mostly Ml2. In spite of the excess of ligand, the reaction does not go to completion because of the relatively low pH. The figure indicates that the initial pH is about 9.1 and drops to about 8.9. This small pH change is the result of the added buffer. To illustrate the modelling power of ReactLab, I will now switch to a data simulation of the same reaction mechanism, but in the absence of added buffer. We have already performed the fit, and as can be seen, obtained the same results for the species spectra and the two forward rates that we fitted previously. We can compare the concentration profiles from this workbook with those in the other workbook. Removing the buffer from the reaction does not affect the initial part of the reaction, as the pH and free L are similar, but due to complexation, the pH drops to pH 8, and this results in slower reactions and a different equilibrium position. Switching to a logarithmic display of the y-axis demonstrates the pH change much more clearly. The ability to incorporate protonation equilibria into kinetic models is a unique feature of ReactLab. It allows the correct modelling of pH changes, thus removing the necessity of using buffers, or if buffers are used, allows the computation of the resulting smaller pH changes. That concludes this demonstration. Thank you for listening.